Swayam Prabha. Digital India. Educated India.
We can also combine various basic blocks. So for example, these all, there's a strictly sequential control flow. So we can combine all these into one and compute gen and we observe that Y, Z are being killed, and we observe here that this occurrence of X is the only occurrence which is not preceded by a definition. This occurrence of Y is preceded by a definition. These occurrences of X and Y are preceded by a definition of Y. X is not preceded by a definition of X. Y is preceded by a definition of Y. And Z is preceded by a definition. And therefore, our gen is X and kill is Y comma Z. So this could also be used and we end up getting the same result. So to understand the effect of these equations, so what are the local data flow properties? Our local data flow properties are gen and kill. Gen says it's something, it's a use not preceded by a definition. Gen contains variables that are used and these use preceded by a definition of the same variable. Kill says there is a definition anywhere in a block. So gen can be seen as upwards exposed use. It is exposed upwards in the sense that it is not covered by an assignment to a variable. So this is upwards exposed use that generates, that begins the liveness, and this kill essentially stops the effect being propagated across a block. Okay, so this is how we perform live variables analysis. And how can we use it? So what can we use it for? We can use it for register allocation. For example, if a variable X live in a basic block B, then it is then it is a candidate for register allocation, because if a variable is live at the exit of a basic block B, what it essentially means is the variable contains a value that is useful. It's required later, and it is useful to store the values in registers rather than fetching them from memory every time. Similarly, it can be used for dead code elimination. In particular, if a variable is not live after an assignment X equal to something, then the assignment is redundant and can be deleted as dead code, which is what we've seen in the optimizing transformations that we saw in the first lecture. Here I have a tutorial problem. The slides contain many problems. I do not know whether I will be able to go over each one of them, but the solutions are also here. And I would urge you to try and perform these analyses, compute solutions yourself, and see for yourself that you are getting the required result. In case you get some other result, please feel free to get back to me at any point of time. You can send me an email and ask me a question about the tutorial, the solution of a tutorial problem, and you can explain what solution you are getting and why your solution is different from the solution that I have given. So let's look at the first tutorial problem. We want to perform dead code elimination here. So this is some program. Again, let's not worry too much about what does this program do. We are interested in seeing what we can do with this particular program. So let's observe the gen and kill. In basic block 1, the gen is empty set. In basic block 1, we are saying gen is empty set. Can someone tell me why this is empty set?
Because C is being read, but it is being defined just before.
Yes. Although C is being read, it is preceded by a definition of C and no other variable is being read. And kill is A, B, C, and variables are being defined. In this basic block, kill is empty set. Can someone tell me why kill is empty here?
There is no definition.
There is no definition, right? There is only read of a variable. So we have gen as a comma m and kill is empty set. In this particular basic block, both gen and kill contain a. Does it make sense? Does anyone have a confusion about how we have a in both kill for this particular basic block? If you have a confusion, this is the time to ask, because if you don't get it clarified right now, you're going to get confused later. You're going to get confused much more later. So this is okay. A is both live, its liveness is generated and its liveness is killed. In basic block 4, again nothing is defined. So kill is empty set. A is being read. So A is in the set gen. In this particular basic block, first of all, we have kept temporaries out here initially. But supposing we include temporaries, even then, we have the variables A and B, which are being read before being defined. Similarly, C is being read before being defined. T1 is being read, but T1 is, the temporary T1 is defined here. So therefore, our gen is A comma B comma C, and kill is A and T1. And in basic block 6, both these are empty sets. Our initialization is empty set at every program point. Okay. Boundary information for this program out of 6 is also empty set, because we're talking about local variables. So let us compute the first round of live variables analysis. I will pause for 2 minutes to give you time to look at this result or compute yourself and see whether you are getting the same result. I think it's worthwhile pausing for a couple of minutes here before we proceed. Please try to do this yourself. If you're able to do it yourself, you will understand the things that are going to come later much better.
Hello, sir.
Yes?
Sir, can you please explain once the local data flow information at block number 5? For the
Block
T1?
number 5. Okay. So talking about block number 5. So can you see that A and B are read before being defined within the basic block? Yes?
Yes.
Right?
Yes.
Yeah. Okay. So for some reason I'm unable to see the name of the person asking the question. Okay.
Yes, sir.
I don't know. Aditi. Okay. Okay. So the A and B are being read before being defined. So therefore A and B must be live, must be generated, must be in the liveness is generated. So they must be in the set gen. How about C? C is being read, but this assignment before it doesn't define C. So C must also be in the set gen. Is it all right, Aditi?
Yes, sir. Yes.
Right? So let's see which are the assignments, which are the definitions. So T1 is being defined. So we say T1 is in the kill set, and A is also being defined. So A is in the kill set. And the interesting thing is the liveness of A is being generated and the liveness of A is being killed. This can happen only if the statement killing A appears after the statement generating the liveness of A. The point of putting this here in the kill set is, effectively it means that if A was live at the exit of 5, then that liveness propagation will be blocked by this particular assignment. It's a different matter that A is made live by this statement. But kill merely says, I'm going to block the propagation of liveness from the exit of this block, basic block, to the entry of this basic block. And that is why A is both in kill and kill and gen. Was that your doubt, Aditi?
Yes, sir. Got it. Thank you.
Yeah. Okay. So I hope that all of you have got these values. I don't think I would like to explain computation of these values. You can work them out later as well if you have not been able to work out.
So I have
Yeah.
one doubt.
Yeah.
So in the fifth block only, so the formula for in 5 would be out minus kill for fifth block, but the out is 5 and the kill is a comma t1. So how do we? Okay, it's a set minus. Okay.
So we also have gen, right?
Yeah, the union with the zen. Okay.
Union with gen, right?
Yeah, it's clear now.
Right? So because we get ABC here in the in, we get ABC here in the out, here in the in, and therefore we get ABC here in the out. The interesting thing is block 3. Block 3 is still empty set because we visited 3. After 4, we visited 3. And then we want to visit 2, right? So, which means that over it once again and find out what is the value. So this, whatever is effectively what is at the in of 2 will be propagated to the out of 3 in the next iteration, which is what we get. So at the out of 3, we get ABCM, and therefore at the in of 3 we M, and therefore at the out of 2 we get ABCM. At the in of 2 we had ABCM anyway, right? So this is the solution that we get, and after this, even if we were to recompute it, there will be no further change. So this is our solution. How do we use this solution? How do we use the result of this data flow analysis? So the interesting thing is to see this, that out of node 5 is empty set, whereas this is defining A. Do you see that? A is not live at the exit of 5, but we're defining A, which means that this is an example of a dead code. So we can, in principle, optimize this and remove this. Okay. Now, once we remove this, we observe that the use of T1 goes away, and therefore this may also be removed. So what is the moral of the story? The observations are that we can repeat liveness analysis on the optimized code and optimize it further. This can continue as long as the code continues to change. Okay. A better approach would be to perform strong liveness analysis, which takes the transitive closure of this information, and it tells us the transitive closure of what is being dead, what is being killed, and it gives us a more precise liveness information. The code needs to be optimized only once. Here we show repeated application only to show the scope of further optimizations. Okay, so we have removed this statement. We have removed this statement, A assignment to A, and we can once again compute live variables analysis. We once again get some information. Observe that this continues to be empty set, and there is an assignment T1 is equal to A plus B. So this can also go away. So this can also go away. So we can optimize this further, and now we have only, and now we perform once again live variables analysis and observe that now we have B which is not live anywhere. In fact, B was not live even in the previous, B was live here. We have T is equal to A plus B. But now that we have eliminated that statement, liveness information has become even more precise. What that means is these assignments to B and see, if you look at node 1, in node 1, we have B is not live. So B equal to 2 is redundant. Okay. C is useful because C is used locally. A is live because of this use. So this is a further optimization that we can perform. So what does data flow analysis involve? Now let's try to generalize from our observations. So it requires us to define the analysis. It requires simulate the analysis. When we say define the analysis, we have to precisely say which variable is live. When we say formulate the analysis, we have to give a mathematical definition, and then we have to perform the analysis. So defining the analysis involves defining the properties of execution paths. Formulating the analysis involves defining data flow equations, which are linear simultaneous equations on sets in most cases rather than numbers. Later, we'll generalize the domain of the values, perhaps not in this talk. And performing analysis involves solving the data flow equations for the given program flow graph. There are many unanswered questions. What should be the initial value? Can we guarantee termination? What is the complexity of this analysis? How many iterations are we likely to require even if we guarantee that it's going to terminate? There are many other questions. Properties of solutions. Does it involve any harmless errors? Does it involve any harmful errors? Is it sound? Is it precise? So these are the kind of questions that we need to ask. And unfortunately, we will not be able to answer these questions formally in this short duration. In my CS 618 course at IIT Bombay, I do these things in lots of details mathematically, but here we will only intuitions. Okay, so we're going to use Jacobi method of solving simultaneous equations, which uses the values from the current iteration whenever possible. The unknowns are the data flow variables in and out. A domain of values is not numbers, and we perform computation in a fixed order over a control flow graph, either a forward order, forward traversal, or more formally it's called reverse post order traversal, or a backward traversal. So this is the method that we will be using, and there are further tutorial problems which I will leave for you to go through. There are several questions, so there are solutions. I would urge you to perform this analysis and check the solutions. Then there is further questions on the results that are obtained on this example. Again, the answers are here, but I will not go into the details. There's one more tutorial problem here, whose solutions are given. Again, there are certain questions. I will urge you to find out answers to these questions. Maybe you can try it sometime in the afternoon. If you have a question, send me an email, or we can have a short meeting. If there are many students who have questions about these problems, there is some extra slot. We might be able to meet just to look at your solutions. But for now, let me proceed. So let's look at choice of initialization. So let's try to answer those questions intuitively. So there are many ways in which we can answer this question. One of the ways is our confluence, our way of merging the information is union. And the identity of union is empty set. And therefore, we should use initial value as empty set. We begin with empty set and let the sets grow at each program point. A revisit to a program point may consider a new execution path. More variables may be found to be live. But the important point is a variable found to be live earlier does not become dead. This is a monotonicity property which guarantees termination. Essentially, we say that the variables can only grow. They can never shrink. A variable can never, if we discovered a variable to be live at one point of time, we're not later going to find it as dead. We do not do this non-monotonic computation. And therefore, the sets will always grow, and therefore, the termination is guaranteed. Now let's look at initialization. So here is a simple program. Let's say we initialize with empty set, and then we compute. In the first iteration, we mark in this block, nothing is live. Here nothing is live, here B becomes live, and here B becomes live. This is our final solution. Okay. In the next iteration, we end up getting B as live here because B is live here. Because of this loop, liveness of B from the entry of this block is transferred to the exit of this block. Suppose we took some other initialization. Suppose we took universal set as the initialization. This being boundary info will remain empty set, but let's say we take this as the initialization, and let's say we start computation once again. So this is empty set. Now this is empty set because gen and kill here are empty. So although we initialized it to A comma B, we got empty set. Then we got A comma B here because we are computing this as a union of this and this, the value, entry value here. So we mark A comma B here as live. We get A comma B here live. We get A comma B live here. We get nothing as live here because A and B are defined. Observe that A is spuriously marked as live. A is not live here. There is no use of A. We ended up marking it as live because we chose a different. Note that this marking A as live is a harmless error. You'll end up keeping it in the register, but you're not going to miss out on the value. If you keep it, if you mark A as live, what's going to happen is you will not be able to eliminate the assignment to A, but it is harmless because it doesn't change the behavior of the program. What would have been wrong is to say B is not live here, in which case you would have eliminated the assignment to B, and then the result would be unsound because you have B undefined here in the optimized program, whereas in the original program, B is defined. So use of empty set guarantees a more precise solution. Intuitively, because we want to compute the smallest set of variables that are live. So soundness and precision of liveness analysis. So let's assume dead code elimination based on liveness information. Okay. So there are two possibilities of errors. One is we spuriously mark a non-live variable as live. So here Y is live, but let's say we mark X also as live. So this is an error. And we want to see whether this is harmless or harmful. So what's going to happen is X is equal to Y plus 10 is dead, but may not be eliminated. This is this error. Solution is sound, but is imprecise. Okay. The other property is spurious exclusion of live variables. So here we have X and Y as both live, but we marked only Y as live. We missed out marking X as live. Here, X is equal to Z plus 10 is useful because its value is used in printing here, but it may be eliminated. This is a harmful error and the solution is unsound. Okay. So how do we define soundness and precision? So we say given L2, which is a subset of L1 representing liveness information, if L1 is sound, then using L2 in place of L1 is sound because we are only going to declare some additional variables as live. It may lead to some error, but the error will be harmless. It will not be a harmful error. Okay. On the other hand, if L2 is known to be sound, we don't know about L1. If L2 is known to be sound, then using L1 in place of L2 may not be sound. For all you know, you may have missed a variable, a live variable, and therefore it may not be sound. Okay. And therefore, the smallest set of all live variables is most precise. Since liveness sets grow, confluence is union, we choose empty set as the initial conservative value. Okay. So let's talk about termination, convergence, and complexity. For live variables analysis, the sets of all variables is finite. The meet operation is union. The sets grow. Sets associated with a data flow variable can only grow. And because we're talking about a finite set, at some point of time, this process must terminate. And therefore, termination is guaranteed. Since the initial value is empty set, live variables analysis converges on the smallest set. The question is, how many iterations do we need for reaching the convergence? That's a question which is hard to answer now, but it is somehow related to the loops and the packages in the program. In particular, formally, it is bounded by the maximum number of packages in any acyclic path. And unfortunately, I will not be able to explain more about it now. But the question is, when we go beyond live variables analysis, do the sets always grow for other data flow frameworks? And what is the complexity of round robin analyses for other analyses? These are some interesting questions. Unfortunately, we will not be able to answer the second question here, but we indeed will answer the first question here when we look at available expressions analysis. So I think it's time for me to pause and take questions. If you have any questions on live variables analysis that we have seen so far, I will be happy to answer them. Okay.